Okay, good morning, or I don't know when you're watching this. This is for your Thermal 2 class. I know that's not the official name. And this is some information for exam 1. And I'm going to talk about first the exam that you took in class, just a little bit about one part there, and then a little bit about the take-home part that you're still working on. Hopefully, you're not watching this after. It doesn't matter. So it'll be 15 minutes, no more. And again, the first part will be related to part D of the in-class problem from yesterday. That's when you took it. And then if you want to skip that part, then you can proceed to the second half or the second part. I don't know how long each one will be, where we will talk a little bit about the take home. So this is what I'm going to talk about for the one yesterday, and this is for the one that is a take home. All right. Okay, so for your in-class exam yesterday, you had a saturated liquid and you had also saturated vapor, and some parts were asking you some information about saturated liquid, some part about saturated vapor. So I have it here. It says for saturated steam at 200, these are the values that you will get from the tables, calculate specific Gibbs free energy, and then because you have to say in equilibrium, the specific or the Gibbs energy for the saturated vapor and saturated liquid were the same. You can find properties for the other one. In that case, will be for saturated liquid, part C. But then part D, the one that you struggled with the most, was asking for the. Can't answer that. I'm sorry. And I think that's important, but it doesn't matter. So it was asking you for the heat transfer, right? So the heat that your substance required to go from saturated liquid to saturated vapor, because it was asking you, I don't have it here because I just have parts A through C, but if the wording, I remember it correctly, it was asking what is the heat transfer required to completely evaporate your system. In this case, it was water. Okay, so I'm going to share my screen here. I'm going to go over that briefly. I'm trying to share the iPad. I really had to answer that phone call. Why do they call me now and not come? It's thinking, so I'm not wasting time. It's trying to share. Okay, so what I'm going to start writing here is I'm going from saturated liquid to saturated vapor, and that was for part D. Okay, so for your for part 1, this is part D. I wanted to go from, you don't have to write any of this down. Okay, this is just in case you don't remember this from your thermal 1. Okay, I'm going from a saturated liquid to a saturated vapor. Why is it writing like that? Saturated vapor. Okay, so you may remember this from before. Doesn't matter if you don't, because that's why this is for. Okay, I start with liquids such as this, but without the orange, all right? And let's say that is just liquid, and we know that this over here is actually compressed liquid, okay? But then I can heat it up until it reaches a saturation temp. In this case, the temperature was given, so the saturation pressure. And after that point, if I add any more energy by heat to it, it will start expanding if I allow it, and it will slowly evaporate. And it will be a mixture before that happens. So I'm going to write that over here. I have the temperature given. iPad, what's wrong with you? And it's going to reach a saturation pressure. I'm heating it up. It's a saturated liquid, which you represent with L, I think, on your table. So after a while, I'm going to leave some space over there. After a while, let's pretend the container is the same size, right? You're going to have saturated vapor, okay, which I think your table represents would be. The temperature is still the same, and the pressure is still the same, because during this process, if I'm fixing one of the two, the other one will stay fixed, and all the energy that I'm adding to my substance, to my system, what it will do is change phase from liquid to vapor. But it doesn't happen just liquid to vapor. There is a gradual process where I have a mixture of the two. I'm going to have some liquid with some vapor on top, okay, while I'm adding energy by heat transfer, okay? So in this process, and we're here, we have a mixture, okay? In the beginning, I have just a little bit of just a little bit of vapor, a lot of liquid, and then it gradually becomes more and more saturated vapor until all of it is saturated vapor, which would be this part over here, okay? So this is the process, and what the problem was asking you is that Q needed to go from, you don't have to write any of this down, okay? To go from L to V, from saturated liquid to saturated vapor. And if I have that in kilojoules, okay, I will have that is delta H. So just using the notation that you have in your textbook, okay, that'll be delta H, where H is enthalpy. This is a review, I guess, and H is the internal energy plus P times V, okay, pressure times volume. So that is, you know, in this process of evaporation, I have the internal energy increasing, I have the pressure staying constant, and I have the volume increasing. So we can use the first law from your thermal one, and you can get to this equation. And then if I want to use, you know, in the case of your exam, if you have specific, okay, like this, specific enthalpy, which is per unit mass, and you have to multiply it by the mass, okay? Where this, the units are kilojoules per kilogram. Okay, so that was terrible at the end. That was part D. What am I trying to write over here? Kilojoules per kilogram, okay? So that was part D. Let me know if you have any questions with that. Now I'm going to move on to your part 2, and I'm not going to do any MathCAD here. I can't sign in. I haven't tried it in MathCAD yet, but I was setting it up. I don't have to write that again. Part 2. So for part 2, you have superheated steam. I'm going to write some stuff down, and maybe you already did this. Maybe it's easy and you already finished it. Maybe it isn't. You know, good students can have all sorts of days. Sometimes it's easy, sometimes it isn't, okay? And it's entering a turbine or turbine, like some people say, okay? And then you have my inlet and my exit. How long has it been? 7 minutes. And then we get some power out of it because that's the objective. That's not an exit or an inlet, that's just power out, okay? And then we have a bunch of given values. We have that at the inlet. Thankfully, we have the velocity. Otherwise, I was trying to figure out how to solve this problem. I'll give you a hint over here. The change in kinetic energy, once you have it in the same units as the changing enthalpy, is very small, okay? The change in kinetic compared to the changing enthalpy. Okay, kinetic energy, right? So here we have that P1 is 20 megapascal, C1 is 500 degrees. I want you to just stop for 3 seconds and say, those are very high values, okay? Those are pretty extreme values. Okay, then we have that the diameter is given, 10 centimeters at the inlet, and then it's also at the exit given with the pressure at the exit, which will be lower, because that's what happens in a turbine, and the energy is decreasing, the energy of the fluid. So we can convert that energy to useful energy for us. And is that it? That's it. Okay, so for part A, it's asking you to find the mass flow rate, okay? Mass flow rate could be mass flow rate at inlet or mass flow rate at exit. They're the same. So I guess there's a hint here. We can find the mass flow rate at the inlet because we have enough information there, okay? This will be the area of the inlet times the velocity of the inlet, and that's volumetric flow rate. And we divide this by specific volume. I don't know how you represent that with in this class, because in my class, Thermal 1, mechanical engineering, we did it like this, all right? Well, that's not how you represent that. So, right, divided by specific volume. So I could do that too, and it's gonna give me the same, A2, V2 divided by specific volume of 2, but I don't have enough information there because I don't have velocity at 2, okay? So here, when you go to part E, no, when you go to part F, you're gonna use this same equation, okay? But you are going to find the specific volume from the table. In your case, you need to find the specific volume using MathCAD. Is that right? Yes, you have to use MathCAD, and you have to use let me see, I'm looking at it here. Peng Robinson from MathCAD. People, I mean, you don't have to use MathCAD. You can use Excel if you want, but I recommend using Peng Robinson because the program is already set up. So you're welcome to use that. That's the comment that I have over here. I don't have a lot of time left. Oh yes, so it's due at 11:59 because I don't have a lot of time left. And you may submit by hand in MathCAD. There's no extra credit for using MathCAD, but you can use Excel if you want. But yes, you will use the Peng Robinson equation. So I'm reading straight from Canvas. And from that, you're going to find the specific volume, okay? Give me 1 second. I'm sharing my iPad still. Okay, I don't have a lot of time left, so I won't say everything I want to say here. But I'm trying to make sure that I'm finding. Yes, okay. So again, you will use, for part A, you will use your MathCAD code, or you can use the one that my dad set up to begin that to find the specific volume. For part E, you find the specific volume from the tables. Okay, for part B, that you have to find a change in kinetic energy. I'm trying to get the units here. Well, this has to be kilograms per minute, the first one, but the second one says a change in kinetic energy through the turbine in kilowatts. So if we find the change in kinetic energy, this is kilojoules. Okay, so actually you have to find mass flow rate times the change in kinetic energy in a way that you have kilojoules per kilogram. Okay, so you have to be careful with the units here. So this will be your m dot that you found times 1/2 times the velocity at the exit minus the velocity at the inlet. That velocity at the exit, you will also find from MathCAD. So I'm going to highlight the things here that we're going to find using the code, and I'll try to give you a little bit more information about that, but just very little. That is my dad. Oh my God, it's just showing right there. The way I call him. Why is everything happening now? Well, wait, all right, see. Now, for the third part, is asking you to find the changing enthalpy through the turbine in kilowatts, but the same thing, if I just look for the changing enthalpy, that is kilojoules. This one is kilojoules per kilogram. And then you would need m dot times delta H to get this in kilowatts, and that delta H will be 2 minus 1 this way, okay? For part D, this very closely related to part C, okay? I'll let you figure that one out. All right, then for part E, you have to find the changing entropy through the turbine in kilojoules per kilogram Kelvin. So that will be this, okay? So not multiplied by m dot. So that one will be at the exit minus the inlet. And for that, you also have to use your code. You have to do it for this, and you have to do it for this. And again, I haven't solved it, but it might also be for this and this. So I don't think that's given, but definitely for 2, you have to do that. Now here, it also asks you to comment on the reversibility of the process. Reversibility of the process, when this is greater than 0, you have an irreversible process, my bad. And then when Sgen is equal to 0, you have a reversible process. And then when the change in entropy, and Sgen are the same, that happens when you have Q equal to 0, okay? And then you have to figure it out. Is Q equal to 0 here? Is adiabatic? Does that mean Q equal to 0? Okay. So then the last thing I want to say is that when you're going to your code, you want to go from your state 1 that is given, that's not an ideal gas, from that to ideal gas state 1, okay? And from that to ideal gas state 2, and from that to state 2 in order to find your properties, okay? So you would use the departure functions to go from here to here, and then from here to here, and then from ideal gas, you would just use ideal gas equations, okay? I hope that's helpful. Let me know if you have questions. Just trying to keep this at 15 minutes. Thank you for watching, and take care of yourself. Where is this? All right, see you later. Where do I sub it? End.